Going to stick to it. This is one of my favorite scientists who's looking at this phenomenon right now, and a great person altogether, Dr. Kevin Knuth. Professor Kevin Knuth.
Your fans.
Professor Kevin Knuth is an associate professor in the Department of Physics at the University of Albany and is the editor-in-chief of the journal Entropy. He is a former NASA research scientist, having worked for 4 years at NASA Ames Research Center in the Intelligent Systems Division, designing artificial intelligence algorithms for astrophysical data analysis. He has over 20 years of experience in applying Bayesian and maximum entropy methods to the design of machine learning algorithms for data analysis applied to the physical sciences. His current research includes the foundations of physics, quantum information, inference and inquiry, autonomous robotics, and the search for and characterization of extrasolar planets. He's published over 90, you heard that right, 90 peer-reviewed publications, and has been invited to give over 80 presentations in 14 countries. But wait until you hear what he has to say about unidentified aerial phenomenon. You're about to hear Science and the Mishandling of Anomalies, Professor Kevin Knuth.
All right, thank you for that kind introduction and kind welcome as well. I'm going to be talking about how poorly science handles anomalies, which we're maybe not so surprised to learn based on our experiences. And you might be looking at this first slide and wondering, is this a scene from Planet of the Apes? No, it's not. Why do I have such a strange picture up here? This picture has a mountain gorilla looking at earthquake lights. And both gorillas and earthquake lights were at one point in time, not too long ago, thought to be myths. Both of them. How does that happen? So science is conservative and careful. And for this reason, it moves very slowly. This is one reason why science is dependable. It's careful. There were consequences to this, though. As Max Planck had pointed out, science advances one funeral at a time. He said, a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. Yeah, it's rather dark, but that seems to be how things progress, actually. So as such, science sometimes makes a mess of things, as we have all experienced with the whole UAP problem. So here's a few of the theories and ideas that were not readily accepted by science. I'll read some of them. Heliocentrism, that's the idea that the Earth goes around the sun. The idea that stars are suns. Big Bang Theory, dark matter, natural selection, Mendelian genetics. Photosynthesis. Photosynthesis was not at first accepted by science. That might be surprising. The germ theory of disease and antiseptic protocols, which was mentioned in the last talk during the question session. And on the other side, atomic theory and the kinetic theory of gases, general and special relativity, quantum mechanics, origin of meteorites, which is interesting because that story is very similar to the whole UAP problem. Continental drift. I mean, how many of you at age 5 or so realized, hey, look, Africa and South America fit together? But that was not well accepted actually, that was an incredibly controversial problem that went on for decades, surprisingly. Earthquake lights, which I'll talk about. And then certain animals, the gorilla, the okapi, the platypus, the Komodo dragon, the giant squid, and the bondeguzu, which was recently verified as being an animal in Southeast Asia. And I'm probably not even pronouncing it right. So these are some of the ideas that were not readily accepted by science. And I'll talk about a few of these in a bit. So the fact that they weren't readily accepted isn't really the issue. Science is slow, and we demand evidence, and we want to be sure that things are right, which is why we can have some confidence in what science actually does know. But what scientists did wrong was that they worked to stop these ideas from being discussed or studied. They derailed the application of the scientific method of these areas of study. They made ad hominem attacks on the proponents of these theories, and in some cases, risked people's health and safety just to express their disagreement with these ideas. This is really problematic. So these theories, instead of just saying that these theories weren't accepted, these theories were ridiculed and worse, and that's really the problem here. And in the last talk, we got to hear why some people react this way to taboo and the fear that's involved. So one example was atomic theory. Ludwig Boltzmann was an outspoken proponent of the existence of atoms. This is in the late 1800s. And he believed that much of nature was statistical, and he developed the notion of entropy based on counting states. And his ideas were not accepted in his lifetime. And Ernest Mach was, I'll use him as an example, and sad to use him as an example because I have a lot of respect for Ernest Mach, and some of his ideas also weren't accepted. But after an 1897 lecture by Ludwig Boltzmann at the Imperial Academy of Science in Vienna, Ernest Mach walked out of the lecture and just said, "I don't believe atoms exist." And for us now, this is kind of funny, right? But because we've grown up with these ideas. Those people who didn't believe in atoms have died, right? And we grew up with the ideas, so we're familiar with it. And he also said, "I can accept the theory of relativity as little as I can accept the existence of atoms and other such dogmas." So he didn't believe in relativity either. Now, sadly, Ludwig Boltzmann received a lot of ridicule for his belief in atoms, and his theories weren't accepted, and he ended up committing suicide. And I think you talked about this in the question session, the antiseptic protocols. So in the 1800s, childbed fever was frequently lethal condition that affected women in childbirth. And it was much more common for women who were giving birth in healthcare institutions than giving birth at home. It was better to give birth at home. Stay away from the doctors. Basically, that's the situation in the 1800s. And at the Vienna General Hospital, one of the largest obstetric clinics in Europe, pregnant women were admitted into one of two different wards, basically depending on which day they arrived at the hospital, because they accepted them on alternate days. One ward was run entirely by midwives, and the other was run by doctors and medical students. And those doctors and medical students were delivering babies in one room and conducting autopsies of dead women in the room next door. I mean, this is cringeworthy, right? and the incidence of childbed fever was much higher in the doctor's ward. So, down arrow. There we go. So Dr. Semmelweis arrived in Vienna in 1846, and he was struck by this difference in mortality rates and asked questions about it and tried to get to the bottom of what's actually going on here, what's different. And it really came to a head when his friend, Jacob Kolechka, cut himself while performing an autopsy, and then he died from a similar fever. The symptoms of that he had after cutting himself were similar to what was happening to these women. And Semmelweis concluded that cadaverous particles, there must be some particles on the dead people that are on the doctor's hands, and they're causing the fever. So he instituted this new rule of washing your hands in a solution of chlorinated lime and water. And he noted that the effect was immediate and dramatic and resulted in a comparable mortality rates between the two wards. However, this advice was not popular amongst the doctors and the students, and many of whom rebelled by refusing to wash their hands between autopsies and childbirth. So, wow, that's really brave to stand up for what you believe in by putting somebody else's life at risk, right? Horrible. And what was the result of this? Well, Semmelweis's contract was not renewed in March of 1849. Basically, he was fired, right? He had to leave. He returned to Budapest, where he made similar observations and recommendations and saw the same effects. He lost his job there, too. And then a few years later, he was committed to a mental asylum, and he died shortly afterwards. But this work gave rise to the germ theory of disease. So this is an incredibly sad example where people's lives were put at risk, and just to prove a point. And it's not really clear what that point is. The point wasn't well founded. It wasn't scientifically founded, certainly not rational. Another example, quasi-crystals, and these are crystals that are periodic but don't exactly repeat. And on the right, you can see a picture of an image of the atoms in a quasi-crystal. So there's proof that there's atoms right there. Boltzmann would love to see this. But in 1982, materials scientist Dan Shechtman observed that certain aluminum-magnesium alloys produced these unusual diffraction patterns, which were associated with what was hypothesized could be quasi-crystals. And he was afraid to publish this. In fact, he delayed publishing for 2 years because he was afraid of what the community's reaction would be to publishing this result. And in fact, another chemist, Linus Pauling, actually quipped, "There's no such thing as quasi-crystals, only quasi-scientists." Ooh, that's a burn, right? However, fortunately, Professor Shechtman published the results and was awarded the Nobel Prize in Chemistry. So it's a strange, the reactions of people in these taboo situations are surprising. They're very emotional, as you were saying, red in the face and sweating and upset. Why? Clearly, they're not behaving rationally. And so rationality is not part of the issue. It's a fear response, and that's really true. And unfortunately, scientists ought to be able to recognize the difference and act accordingly. But I don't have any problems pinning these really mean quotes to these scientists. If you're going to praise them for their successes, you should remember the bad things they did to hurt other scientists and impede their successes. So one that really gets to me is earthquake lights. Earthquake lights are lights that appear before or during earthquakes, and sometimes have been conflated with or called UAPs or UFOs. And there's some conflation there at times. And I was at NASA Ames in the early 2000s, and I met Friedemann Freund there. We were both presenting our results at a poster session. And his poster was next to mine, and his poster was on earthquake lights. And at the time, I didn't know what earthquake lights were. And so when there was a bit of a lull in the people coming by our posters, I asked him and talked to him, what are earthquake lights? And he said, well, for centuries, people have been reporting strange lights that occur before and during earthquakes. And it's not clear whether these are real or not. And some people have claimed that they're not real, that these people are in an earthquake, they're hysterical, they're seeing lights, it's all psychological, right? And this was the claim. However, Dr. Freund believed that these were actually real effects, and he wanted to study them. So he theorized that a piezoelectric effect, pressure on rocks, is going to create potential differences or voltages across the rock that can cause current to flow. And these will create, in situations where you have high pressure in rocks, you can create electric fields strong enough that will ionize the air above the ground and create lights. And that was his theory. And he was doing experiments by taking columns of granite and putting it under pressure and measuring the electric fields and wanting to do experiments like this. And and he felt that if this was true, then you should be able to measure electric fields and maybe detect earthquakes before they happen. So what do we know about earthquake prediction? Well, earthquake prediction is nonsense. That's what you learn what you learn in geology, and that's what you learn if you go to the USGS website. This is actually a screen from their website. Can you predict earthquakes? No, period. Neither the USGS nor any other scientist have ever predicted a major earthquake. We do not know how, and we do not expect to know how anytime in the foreseeable future. Well, that's certainly the case if you don't ever study it. That's a self-fulfilling prophecy right there. We're not going to study this topic, and we don't expect to ever figure it out. Well, yeah, that makes a lot of sense. So if you read on, it's really pretty horrible. Yes, some people say they can predict earthquakes, but there are reasons why their statements are false. One, they are not based on scientific evidence, and earthquakes are part of a scientific process. For example, earthquakes have nothing to do with clouds, bodily aches, pains, or slugs. This is the list of things that Friedman Freund isn't studying slugs, he's studying piezoelectricity and rocks. This is already way off, right? Two, they don't have to find all of the three elements required for prediction. Three, their predictions are so general, there'll always be an earthquake that fits. And so on. So it keeps going, and it's quite clear that they are not at all going to consider the problem of earthquake prediction. Worse, you can't even publish papers on earthquake prediction. You can't present them at conferences. He was never accepted into conferences, always rejected. So this is a big problem. So time passes, a little bit of time, about 20 years passes, and with security cameras all over the place, earthquake lights have been recorded by security cameras. They've also been observed from orbit. This is hopeful for those of us in the UAP field. Like, we might actually get evidence too that other people might eventually believe. So here's an article from New Scientist, 2023, 20 years later. These bizarre lights in the sky hint at a way to predict earthquakes. Semi-mythical earthquake lights may be accompanied by changes to the Earth's magnetic field. Now researchers say these changes could be used to forecast major tremors. Right, 20 years later, I'm going to get a bit emotional because I feel very strongly about this. I learned about this 20 years ago. And in those 20 years, 678,000 people have died from earthquakes. How is that right at all? I have a problem with that. That makes me angry. We could have been studying earthquake lights and these electric fields for 20 years. Imagine what would be possible. 20 years of study, well-funded. We could have maybe saved 600,000 people's lives. It's a big deal. The next earthquake that you see on television, you see how many thousand people die. They could have been saved. But science is conservative and careful. And science advances one funeral at a time. And what about these 678,000 earthquake-related funerals? What if they were scientists? Think how far ahead we'd have gone. But no, that's not the case. Instead, we have the Earthquake Hazards Program. The USGS monitors and reports on earthquakes and assesses earthquake impacts and hazards and conducts targeted research on the causes and effects of earthquakes. We undertake these activities as part of the larger Earthquake Hazards Reduction Program. We're not going to predict them. We're just going to try to reduce the hazards. Can we do better? I think we can do better, and we should be doing better. So we're here to talk about another problem that has not been accepted by the scientific community, and that's UAP. And one way that I've found to get my fellow scientists' attention is to talk about the flight hazards of UAP. The fact that pilots see them. Airline pilots see them. Airline pilots see them when you're in the back, riding, eating your pretzels. That happens. And sometimes these pilots are worried and concerned. That's a problem. And that's a problem that makes my colleagues nervous because they fly a lot, because they're scientists and they're always going to conferences like this one. So this is an easy thing to convince a scientist that it should be studied. And this is what I found to be useful. Saying pilots ought to know what's in the air. And if they don't know what's in the air, that's a problem. And nobody's going to argue against that. And I found that to be useful. So I can get them to admit that we should study it. But then they'll very quickly say things like, oh, I don't understand why everybody thinks they're alien spacecraft. And whenever I hear somebody use that phrase, I don't understand X, I get stuck on I get stuck at that comma. And you hear people say this all the time. I can come up with all sorts of political things, or I'll try to come up with something less controversial. I don't understand why people think they're being abducted by aliens. Well, the problem here is clearly, and you've stated it already, you don't understand. So why don't you focus on that and then try to solve that problem, and then you can circle back and try to look at the rest of that sentence. That's how I look at this. And that can be applied to anything anybody says about, I don't understand. They're telling on themselves. They've made it very clear what the situation is. And I think that sometimes pointing that out to them is helpful. So we're here to talk about UAPs. Here's some pictures of UAPs. And let's try to understand why this is so difficult from a rational perspective. Carl Sagan is well known for this aphorism, extraordinary claims require extraordinary evidence. This one drives me nuts. And I'm sure it drives all of you nuts as well. And why? Because it's ambiguous. It's not clear what extraordinary means, and it's not clear, the other second arrow should also be on extraordinary. The two extraordinaries are ambiguous. What do you mean by extraordinary claims, and what do you mean by an extraordinary evidence? And it's horribly misused, basically, to shut down rational discourse. So you're not allowed to talk about UAPs unless you have some smoking gun extraordinary evidence. And what is this evidence going to be that people are going to pay any attention of? I've joked that it would have to be a UFO landing in Central Park and authorities dragging an alien, kicking and screaming off of it on live television. It would have to be something of that order before everybody is like, oh, wow, what's going on? And you're not going to get that kind of evidence. And we don't use that kind of evidence in science. The evidence that's used in science is usually very little, very tiny things. I study exoplanets, planets orbiting other stars. And we do a lot of this by looking at the light coming from the stars. And we look to see how much the star dims as the planet passes across. And we use the way in which the star dims to learn about that planet. That's a tiny bit of evidence. It's the amount of dimming that you get for a planet passing across a star is like 1/1,000,000th of the total amount of light coming through. The evidence is small. And we do that regularly, and we're happy with it. But we're not happy with the little bit of evidence we get for UFOs. So there's a problem here. The way we handle problems in science is we compare the probabilities of different models based on data. And we call this statistical model testing. We like to think that we rule out hypotheses. Rarely do you get data strong enough to rule out a hypothesis. What you really have is you have data that supports one hypothesis more than another. And you want to quantify how much more it supports that hypothesis. So we're going to do a little bit of math here, and I'll try to walk you through it. So here I'm showing On the top of this ratio is the probability of one model and some data given your prior information, compared to the denominator, which is the probability of a second model given some data and your prior information. And if the probability of the first model is much higher than the probability of the second model, then this ratio is greater than 1. And you'll favor the first model. So let's see what happens with this. We can use the product rule in probability to write the joint probabilities on the left in terms of the second expression. So we can write this as the probability of the data given your prior information times the probability of the model 1 given the data and your prior information. And then likewise do the same thing for model 2. And this can also be written because the probability of M1, model 1, and the data is the same as the probability of the data and model 1, so you can switch them around, and you can write it the other way around as well. And those are all equal. Now you can see the probability of the two datas given your prior information cancel, so we can get rid of that and simplify things a bit. And now we're left with this piece that says that the probability of model 1 given your data and your prior information can be written in the way on the right. And so this ratio between the two can be given by this longer expression. So this is basically how we're going to compare the probabilities of two different models based on the data that we receive. And we'll look at this in terms of two particular models. We'll consider model 1 to be an extraordinary model, something that's going to be surprising to people. Perhaps that the object that you're looking at is an alien spacecraft. Right? There's a extraordinary model. Compared to a more prosaic model, which is that it's a Chinese balloon. We'll use those as examples. So I'll just use M for the prosaic hypothesis. Everything's normal and happy, whereas I'll use extra to represent the extraordinary hypothesis. So we can write all I've done is replaced M1 and M2 with extra and M. So not much has changed here. So this term here is a ratio of what are called prior probabilities. This is the probability of your extraordinary model given just your prior information. How possible is this extraordinary model based on what you know about anything? As compared to what's true about the prosaic model based on what you know about anything. And this is basically what you believe before you have any data. The second term considers what's called the ratio of the likelihoods of the data. These are the probabilities that the model you're considering could have resulted in the data that you have. So if we're going to favor the extraordinary hypothesis, then this ratio on the left had better be greater than 1. You need that the probability of the extraordinary hypothesis has got to be greater than the probability of the prosaic hypothesis. So what does that mean for the right-hand side? Well, what happens typically is you have a rational yet very skeptical person, and they might assign a very small probability to the extraordinary hypothesis. We use Greek letter epsilons for tiny numbers. So this is a very small number. It can't be 0. You can show using probability theory that 0 breaks everything. Once you assign a probability of 0 to something, you can't learn about it anymore. So it turns out that assigning epsilon is maybe theoretically better, but it's not practically better, and that's what I'm going to show you here. So assigning a crazy small probability to a hypothesis does not help you, and this is what we're going to walk through. So this ratio on the right, the first term on the right, the probability of the extraordinary hypothesis, the ratio of that probability to the probability of the prosaic hypothesis is going to be assigned a very small number by a skeptic. And that's what we mean by an extraordinary claim. That's a way of quantifying an extraordinary claim. So an extraordinary claim is one such that its prior probability is really, really tiny. I once was in a conference, a statistics conference in Mississippi. And we were having the conference dinner, but it was kind of in public, so there were other people. It was in a restaurant, but there were other people around. And I sat down at one of the tables a little late. I got my food late and sat down at one of the tables with some of my colleagues. And they were having a discussion on whether they believed in God or not, which is a great discussion to have in Mississippi. They were from Europe, and so this was, and so I sat down, I was like, oh, good Lord, this is what we're gonna talk about. And then they asked me what I thought, and I said, I'm agnostic. And one of my friends from England was like, that's a cop-out, you have to choose. And I was like, I have chosen, I'm telling you, I don't know. And he goes, and he goes, no, do you believe it or not? I said, well, I'm not going to assign a probability of 1 or 0 because that's ridiculous. And he knew this, and he goes, all right, so it's not 0. How about epsilon? And I was like, sure, epsilon, whatever. Can we move on to another topic? All right, so for this ratio to be greater than 1, on the left side, I need something greater than 1 on the right side because they're equal, right? So if I'm going to assign an epsilon for the extraordinary hypothesis as probability, then that ratio of the probability of the datas had better be greater, much greater than 1 over epsilon. So the epsilons cancel and I get a number greater than 1, right? That's the idea. So that ratio has to be much greater than 1 over epsilon. We can then write that ratio, if we write that as being greater than 1 over epsilon in the lower right, you can rewrite things as this means that the probability of the data given the extraordinary hypothesis it better be a big number, 1 over epsilon is a giant number, times the probability of the data given the model. So that means your extraordinary hypothesis had better predict that data much, 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 much better than a prosaic model. And that's what we mean by extraordinary evidence. So now we've basically quantified Carl Sagan's aphorism. All right, so now we have a better idea of what we're dealing with. And another way of putting this statement is to quote David Hume from 1748. And when he had a treatise on miracles. What is the probability of a miracle, right? So he said that no testimony is sufficient to establish a miracle unless the testimony be of such a kind that its falsehood would be more miraculous than the fact that it endeavors to establish. So basically, if a miracle is going to be true, then the probability of that being true it's going to have to be such that the probability that the evidence for that miracle is an error has to be much greater than the probability of the miracle being true. Otherwise, you're just going to believe everything's an error, right? So somebody sees the Virgin Mary in a piece of toast, right? And now is the probability that that's really the Virgin Mary based on the probability that somebody's in error in some way. You've got a toaster that actually has a picture of Virgin Mary in the on the heating coils. If that's more probable than the Virgin Mary actually appearing in the toast, you're going to believe that that's what's going on in the toaster before you believe that that's a Virgin Mary. So that's the way to think about this in terms of miracles, perhaps. The silly example. All right, so the problem is that even if your extraordinary hypothesis best predicts the data, you still have to have that it's got to be much, much greater than the probability that an error predicts the data. And that error, the probability of that error predicting the data has to be less than this probability epsilon. So this tiny probability that you've assigned for the extraordinary hypothesis, it's going to have to be even less probable for an error to support that data for you to even believe the extraordinary hypothesis. The problem then is that if that probability for the extraordinary hypothesis is so small, then almost no amount of data will be enough to prove the extraordinary hypothesis. You'll always believe it was an error. That'll always be more probable. And we give this a name. This is a maladaptive behavior that comes from this, and it's called denial of the anomaly. The anomalous data is just simply disbelieved because something's clearly an error. These things are not making sonic booms when they're traveling through the atmosphere at 40,000 miles an hour, so something has to be an error. That's much more probable than you have a craft traveling through the air at 40,000 miles without a sonic boom. That's the thinking. And it's actually rational if you believe that it's very improbable to have a craft moving through the air at a very high speed. As one of my good friends says, a sufficiently motivated skeptic can deny anything. And I love that quote because it's very true. You just make epsilon small enough and you can deny everything. It's the probability that it's an error is much greater, always going to be much greater. But then you can never have enough evidence to learn about that hypothesis. So too much certainty is a bad thing. I mentioned that assigning zeros is bad. So this is a theorem called Bayes' theorem written out here. It's the probability of hypothesis given the data and your prior information equals your prior probability of the hypothesis just given your prior information, times a data-dependent term. That modifies. So the term on the right on this equation modifies your prior beliefs. And that's how you're learning. This is a learning equation. And this is what's used in machine learning to get our results. So if you set the prior probability for the hypothesis to be zero, there can be no alien spacecraft on Earth, period. Then no matter what data you get, you're always going to believe the hypothesis is zero, probability of the hypothesis is zero. That's why setting things to zero is bad. Equally bad to set it to 1. So you can rearrange things and show that that's equally bad. But we've now seen with epsilon, that's also bad because if your epsilon is too small, then there can never be enough data to actually learn about the hypothesis. So before I go here, so that's the important point, really. What is your goal as a scientist? Is your goal to prove that what you believe is right? Is that your goal? Or prove that what you were taught in school is right? Or is your goal to learn the truth? If your goal is to learn the truth, then you don't ever want to assign a probability that's going to make it so that for some hypotheses you could never possibly prove them to be true. That precludes you from possibly learning the truth. That's just an irrational thing to do. And that's really the problem here. That's what we see happening. So scientists are trained to be skeptical. You know, the purpose of skepticism is to avoid mistakes. And I've now used the fact that skepticism works both ways. One should be skeptical of wild claims, but one should also be skeptical of the wild idea that we pretty much know everything already. That's a wild claim that we don't have proof for, we don't have evidence for. And a lot of scientists seem to believe this. We pretty much know everything already. That is actually not true, and we know it's not true. which makes the claim even more ridiculous. We do have evidence that we don't know everything already, so I can prove that's not true. So healthy skepticism is one that will help you avoid assigning prior probabilities that are too extreme. You don't want your epsilon to be too tiny. You want to entertain the possibility that there could be something strange in the sky. That has to be the situation. Otherwise, you can't learn about it. So really what needs to be done is people need to reevaluate their prior probabilities and be more honest about them. I'm skeptical of your skepticism. Another thing we need to do is consider all the hypotheses when solving problems. Because just comparing two hypotheses isn't enough. Technically, you should be comparing all of them, infinite numbers of hypotheses, which really isn't doable, but you have to cover as much as you can then, right, practically. I love this quote from Winnie the Pooh. So Eeyore has fallen in, and they're going to swoosh him to the shore by throwing rocks in next to him and making waves and swishing him to the shore. And so Piglet gets worried. Supposing we hit him by mistake, said Piglet anxiously. And Eeyore says, well, supposing you missed him by mistake. Think of all the possibilities, Piglet, before you settle down to enjoy yourself. And I think about this, every time I think about considering all the hypotheses, I think about this quote. It's clearly a loose association in my mind and probably says more about me than anything. So probability theory requires that we consider the space of all potential hypotheses before we compute the probabilities of those hypotheses. And very often we get things wrong because we didn't consider the correct hypothesis. This is very possible in what's going on with UAPs. There are many hypotheses that we haven't considered and maybe haven't even come up with yet. And those could be the hypotheses that are the solutions to the problems. Bad things happen when you don't consider the correct hypothesis. And here's a great example from Penn and Teller, the two magicians. Penn Jillette said, magic does not fool you because you're stupid. Magic fools you because it's stupid. I'm going to let them demonstrate what they mean by that. But you'll see what happens when the person that they're playing tricks on doesn't consider all the hypotheses, right? So this is my video here. So we'll see if I'll try the downer. Yeah, so you see bad things happen when you don't consider all the hypotheses, right? And it's the stupid ones that you don't consider because you don't expect they're going to happen. And that's of course what they're doing. For my 50th birthday, my wife had arranged a party for me and hired a really good professional magician. He was on the Today. She saw him on the Today Show, and she hired him, and he played at our party he just did tricks for us all night, individually, which was amazing tricks. But he did something like this for one of my friends where we all could see what was happening. He held a roll of toilet paper, and then he did something and just threw it over her shoulder. And it was so ridiculous. We were laughing so hard because it was really silly to see something like that happen. So considering all the hypotheses is an important thing to do. And that's what skeptical scientists are not doing when they're not considering the extraordinary hypotheses. And so that happens there, but it also happens that we don't consider all the possible hypotheses in some of these problems, and that's difficult. It's overconfidence. Science often believes that they know everything, so they think they have this one peak of high probability and everything is in this area where this high probability is, and this is what they believe they know. And very often we have machine learning algorithms that basically climb these probability peaks to look for the high probability solutions, and they're called gradient descent algorithms. These are widely used. But for people who are well-versed in machine learning, we know they don't always work well. Sometimes they end up on the wrong peak. where there's a higher probability solution somewhere else that they didn't find. And so what happens, the space usually really looks like this, peaks all over the place. And what you really need to do is you need to use an algorithm that explores the space, tries other hypotheses. And so these are one class of algorithms that works well are Markov chain Monte Carlo algorithms that will always move away from a peak. They'll climb peaks, but then they move away from them. And that's useful. So you're going to try many hypotheses and consider many possibilities. And so scientists ought to be doing this as well. They ought to embrace the exploration. They're explorers. Explore. Stop thinking you know everything and that it's all been discovered already, because it hasn't. So go exploring and see what happens. Let's test the possibility. What if these are alien spacecraft? What if they are plasma life forms? What if they are strange things that we haven't discovered yet? That's exciting. Why is this not happening? It ought to be happening. And scientists who do machine learning know that you ought to be exploring. They will argue with other people who use gradient descent algorithms that those algorithms are crap. You need to be doing this. But why aren't they doing this in their own minds? But I don't have the time and energy to consider those hypotheses. I have to consider the ones that I think are most probable. But that's what a gradient descent algorithm does. And we know that fails often. So my response usually is, well, maybe you aren't as interested in discovering the truth as you claimed. You're just wanting to solve the easy problem. and you're not necessarily going to solve the problem. But you don't have to do the work, but you should certainly support it being done. Another thing that's important is you should learn from all available information. To not use all the information available to you is just silly. So some of the information that's available, especially in UAP studies, is anecdotal information. And I like that Professor Nolan calls it pre-data. I think that's a good name for it. It's useful for guiding one's thinking about the problem. There are a lot of people who have seen these things, and some people maybe have actually seen them up close. And that's useful information, especially if you want to figure out how to study them better. Take advantage of that information. Take advantage of all the information you have available. Another friend of mine, he had this wonderful quote once. He's 20 years older than me, and he will sit through a conference all day long and listen to every talk, even the talks by the graduate students. He'll listen and he'll take notes for all of them. I don't know how he does it. I don't have the energy for it. I get saturated after about 3 or 4 hours. But he'll do it for 8 hours. And I once asked him, I was with him and somebody asked him, why are you sitting through all of these talks? And he said, well, I consider myself to be sufficiently intelligent to learn from anyone. And I thought, oh, that's very good. Yeah, I can learn from anybody. And I think about this quote when I think about people saying, well, that's anecdotal information. And like, yeah, and you can learn from it. I'm intelligent enough to learn from it. And another thing we need to do is reduce the probability of error. You need that error probability to be much smaller than that tiny epsilon. So you have to reduce the error as much as possible. There's lots of ways to do this. One way, if you're going to be trying to collect data from UAP, multiple independent disparate pieces of evidence. We model this after multi-messenger astronomy, where you use many different instruments, many different imaging modalities, multiple observation points, multiple independent observing groups. These are all ways to reduce the error. And then another way to have some success is to divide and conquer these challenging hypotheses. So rather than focus on a hypothesis that people are going to consider as extraordinary and give a low probability to, you can focus on things that are not as extraordinary. You can focus on characteristics of the objects And some of those characteristics are not necessarily as extraordinary as the extraordinary hypothesis, and you can make headway this way as well. So these are some strategies for success. Once you know what the problem is, rationally what the problem is, not emotionally, that's a whole different problem, as we learned in the last talk. But rationally, once you know what the problem is, you know that you can see how to best handle this. Skepticism works both ways. And keep that in mind when I'm really annoyed when you start talking about UAPs and somebody goes, I'm skeptical. And if it's a scientist, I want to just say, of course you're skeptical. You're trained to be skeptical. But the fact that you're telling me that means you're actually telling me something else. You're actually telling me, I don't believe in what you're going to tell me, and I'm only going to listen for a few minutes, and then I'm going to tune it out. That's really what they're saying when they say I'm skeptical. I'm skeptical in the idea that they actually want to know the truth. They're certainly not exploring to find it. Another way to succeed, to do better, is to relax one's prior probabilities. You should be skeptical of your own beliefs. You should be as skeptical of your own beliefs as you are of somebody else's beliefs. There's nothing special about you. You should embrace exploration. We scientists are explorers. You should be exploring. Consider all the hypotheses, and you should support the exploration of different ideas. We should try other theories. We might not have the best theories of anything. We need to accommodate information, be sufficiently intelligent to learn from anyone, treat anecdotal information as pre-data, consider everything available, reduce the probability of error, take multiple measurements, multiple observation points, multiple observing groups, and consider hypotheses that are break hypotheses up into bite-sized chunks that you can handle, each one separately, and that will make it a bit easier to make progress. I'll finish with a quote from Boltzmann. Who sees the future? Let us have free scope for all directions of research, away with dogmatism, either atomistic or anti-atomistic. So there we go. Thank you.
Fantastic job, as always.
Thank you.
Yeah. How about that lecture? Everybody followed all the math, right? You guys have those equations committed to memory? No doubt. Okay, all right. Just wanted to make sure. I have a few updates, by the way, about some issues we're having with the Whova app here shortly. But first, let's get into a few questions with Dr. Knuth. We heard a lot about skepticism and what that is, how it can be applied. You know, I said even last night during the opening statements that skepticism is necessary. It's a crucial tool for the scientific process, but sometimes we mean different things by skepticism. This question is in line with that, Dr. Knuth. If we are open-minded, such as assuming 50% prior probability, does this minimize the amount of positive evidence we need to prove a hypothesis such as UAPs exist?
Yeah, if you're going to increase your prior probability, then the likelihood, the predictive power of that hypothesis can go down, and you'll get the same product. So that's true. So assigning too high of a prior probability for something that you don't know anything about is also foolish. So there's and assigning these probabilities is subjective. So there's a delicate balance there. And that's a hard thing to strike. You want to assign a prior probability that's somehow reasonable, somehow conforms to what you believe. And if there's a way of computing what you ought to believe, then that's helpful. So to this effect, I had recently given a talk at a conference in England. It was a SETI conference, or a SETI session at an astronomy conference on galactic colonization. And one of the things that struck me about this idea is that if you asked a scientist what they thought about the possibility of extraterrestrials colonizing other star systems, you get wildly different results. Some people say, oh, yes, of course it's possible. They should be able to traverse the galaxy and populate the galaxy in something like 1 million years. Or you'll get people saying, on the other hand, you'll get people saying, totally impossible, probably can't even make it to the next star system. Everybody would just give up and nobody's going to go anywhere. So you get wildly different results. What ought we believe if that's the case? It's not clear. So what I did is I worked out simulations where I simulated 1 million societies, all with different characteristics, and found how well they can colonize other star systems. And then I used those simulations to inform my beliefs on what I expect somebody coming to Earth to be like. And that's one way to try to handle this prior probability issue. Find out what you actually believe. Don't just make it up off the top of your head. In this case, I'm using my knowledge of physics to try to figure out what I ought to believe about galactic colonization. And doing the simulations, it turns out it's possible. And you don't have to go faster than the speed of light. You don't have to go, you can travel at 20% the speed of light and do very well, actually. So.
Being someone who laid awake all night worrying about these things, I feel very comforted to know this. Now, here, sticking with the skepticism side of this, Professor Knuth, what should we do when scientific skepticism is weaponized into popular campaigns to suppress scientific inquiry? An example this questioner provides is, for instance, if we see fairly skewed or biased opinions that are expressed on Wikipedia where a narrative is sort of controlled, how do we combat that?
Right. I think that the best way that I know to combat the weaponization of skepticism is to be skeptical of them and point that out. I'm skeptical of your beliefs, and I'm skeptical of your skepticism. I don't think this is exactly skepticism. I think there's more going on here. There's an emotional element to it, which is not a component of skepticism. And I think that calling people out on that is helpful. That's one thing I tried in my sole presentation was, I'm skeptical. I put that on the first slide, and I did that on purpose because that's what I hear when I first talk to a scientist about UAPs. So I'm just going to start my talks this way and see what happens. And I think that's maybe useful. We can weaponize skepticism too. So
I take a different approach. I'm not skeptical of skeptics. I just don't believe in them. Professor Knuth, does science consider witness testimony as evidence? I hear from people who say, I saw extraordinary things in the sky. I presume that we'll hear about this a little later with the database project. In fact, I'm currently building a database myself that's primarily witness testimony. But the questioner asks, we know legal communities use witness testimony. Why not the science community? Is it not data?
Science does use witness testimony. It depends on the field of science. Psychologists use witness testimony all the time. That's pretty much all you have in some cases. Medicine uses witness testimony. When they have that long list of symptoms that or side effects that this wonderful medicine is going to give you, week long of diarrhea and blah, blah, blah. This is all coming from witnesses telling you what happened. The doctor wasn't there measuring how bad your diarrhea was. I mean, I'm sorry, that's a horrible example. But I'm hoping driving the point home, I'm trying to drive the point home. It depends on witness testimony. And you have to believe the witness to some degree. Sociologists use witness testimony. Political scientists also use witness testimony. These are all fields that use witness testimony. And like I said in the talk, it's silly not to take advantage of information. You can take into account witness testimony. You don't have to believe it 100%, and you can go from there.
Professor Knuth, I had a colleague of mine who works more primarily in engineering. And when he heard I was building a database, he had said, well, it's useless because, frankly, the best thing we can do is, rather than worry about witness testimony, we just need to train our instruments on these phenomena. If we can't collect it with sensor data, it's irrelevant. So this question addresses that. To avoid conflicts and other negative attacks on scientists, do you think it would be better if humans were completely removed from the scientific investigation process in favor of replacing them with artificial intelligence agents, algorithms capable of performing scientific analyses, and thus humans would simply be spectators in the future?
That's a good question, and that goes a lot further beyond the UAP problem. I'm not sure how I feel about it. Science is a human endeavor, and I was born in the 1900s, so I feel that let's leave it to the humans, and we can use AI to help us, but I think this is still a human enterprise, and I think that's. But I was born in the 1900s, so what do I know?
It is still a human enterprise for now. A question from our audience here. Given all the problems with perceptions, should we even use priors? Instead, could we assume our expectations are likely wrong and then use empiricism to establish truth, i.e. seeking with fresh eyes?
Right. Well, in doing these calculations, you eventually need prior probabilities. But if you want to assign them empirically, one way to do that is through simulations, like I mentioned in my work on galactic colonization. So there are ways to, in some cases, empirically assign probabilities, and that may be helpful sometimes.
Here's a question. How can we better address unexplained phenomena for which we lack the tools to measure and describe? It is a bit presumptuous to think that all of our sensor capabilities, effective though they have proven to be in detecting these anomalous phenomena, they can detect everything about this phenomena. So the question again would be, is our scientific paradigm likely to be incomplete as we have seen in its evolution throughout history? Surely we ought to move past the notion that something should be dismissed or derided because our methods, and maybe our tools as well, cannot explain the data. How do we strike a balance?
Yeah, that's a good point as well. There is a unappreciated relationship between theory and data. You have to have some kind of theory to put the data in context. And you do that every time you're analyzing data. You're always analyzing data in the context of some theory. And if you have that theory wrong, your conclusions that you'll draw from the data can also be wrong. So you can run into problems. So I'd come up with an interesting example that I'll try to explain. So Michelson, Morley did an experiment in the 1800s to try to measure how fast Earth is moving through the ether. The ether was hypothesized to be the material through which light travels. And so what they did is they measured the speed of light in different directions, and they found that it wasn't any different. It didn't matter which way whether the Earth was moving or not. So that was their finding, and that then helped lead to the theory of relativity, which was an advancement for us, right? So consider what would have happened had Michelson and Morley lived in the 1600s, when we were still considering the two models of geocentrism, where the Earth is the center of the universe, and heliocentrism, where the Earth goes around the sun. And they did their experiment in that context of whether is the Earth going around is the Earth stationary and the universe goes around it, or is the sun stationary, or does the Earth go around the sun? That's the context. And now they do their experiment, and they find that the Earth is not moving, and they support geocentrism. So that experiment in that context would have supported the wrong solar system model. And you end up with a wrong path, as opposed to what happened in the 1800s, where it actually showed that the ether model was wrong and then led to special relativity. So you can have wildly different results based on the context in which you're observing your data. So it's not just about collecting data. Data has to be interpreted in a context, and that makes things a lot more complicated.
Professor Knuth, we talked about that quantity epsilon a little earlier. Let's address that one in this next question. It seems that there is still subjectiveness and bias, as epsilon is a parameter that is being assigned by the analyst. So the statistical analysis appears to depend on the person that is doing the analysis. Is there any way to eliminate the human bias when selecting or choosing the epsilon parameter? Good luck.
Yeah, this is a long debated issue in probability theory, and this was a big problem in as Bayesian statistics began to be used more, because in Bayesian statistics you assign prior probabilities explicitly, and those assignments are usually subjective. They depend on the person making those assignments. The best situation is that, what you're trying to solve for is the product of your prior probability, which you knew before you had data, times a data-dependent term, which is what we call the likelihood. And what you usually hope for, and this is what often happens, is that the data is so informative that that gives you a very strong likelihood term. And it almost doesn't matter what you assign in your prior probability. The data basically drives the whole equation. That's usually what happens, and in most of the problems we work on. And so it usually is the case that the prior probabilities don't matter that much. The times when they matter a lot is when the data is not that informative, and then the prior probabilities make a huge difference. And that can be entirely subjective in some cases, and that's a big problem. Nobody knows a way around that, because these equations are describing what we know. And if you can't quantify what you know, you're stuck, right? So you have to do the best you can. It becomes subjective.
Handled masterfully as always. And now for dessert. A colleague of yours, I suspect, sent this one along. Great point about Mach. However, we have to be careful to understand that Mach's reasoning was behind his rejections of atomic and relativity theory. For example, Mach was an empiricist and sought to ground all science in experience. He was a philosophical relationist regarding space-time, which opposed the ontology underlying Newton's theories. Exactly what I thought. How was his rejection motivated by these deeper philosophical commitments?
Right. Well, that's part of the difficulty. Mach had different ideas about space and time, and there was no direct evidence of the existence of atoms. I mean, nobody had ever seen them, right? And they were too small to detect, and so it was difficult for him to accept these things. The evidence was all indirect. And this is often the case in science. As I was saying earlier, the amount of evidence we get for something usually is very tiny. And usually you get many pieces of tiny amounts of evidence and put that all together to build up a theory. And which is why it's always strange when I hear somebody like Michio Kaku saying, there's no smoking gun. Well, no, there never is a smoking gun. There wasn't a smoking gun in Boltzmann's time, and which is why Ernest Mach didn't believe in atoms or relativity. And that's why I felt bad picking on him a little bit, because he was not being entirely unreasonable. And so it's difficult.
Indeed. We've got a bunch of excellent questions. Of course, time is somewhat limited. Let's try and get just a few more of these in here. We saw that breakdown of what we mean by and how we sort of quantify extraordinary evidence when we're dealing with that. This question addresses that issue. In the face of extraordinary evidence, wouldn't it be likely that the probability that the scientific audience, maladaptive behavior, means that no objective scientific learning is capable and really is zero? How then do you deprogram the failure in perception, which is the cause for a flawed paradigm? What approach to amending the scientific method would you propose to overcome the bias?
Oh, there's a lot to parse.
Well, let's break that down really quickly.
Yeah.
I mean, if we think about the idea of paradigm shifts, right? Scientific advancements that have to occur in advance of a change in thinking, which establishes a new approach in science. What has to be changed now to facilitate that?
Right. Yes. So Yeah, because looking at data requires having some theory to put it in context. We have to consider other theories in some ways, right? And this is a difficult thing for anyone to do. Basically, forces you to perform these worldview changes. And I've talked to my friend and colleague Wes Waters about this a great deal, and that if there's ways to facilitate, to help people along in changing their worldview, that's a useful thing to do. So I'll go back to the extraterrestrial hypothesis just because it's an easy one to give an example. So why is it so hard for people to believe in the extraterrestrial hypothesis? Well, one is it's hard to believe that that you can travel that distance. The interstellar distances are vast, so that's hard to do. Would anyone bother doing it is the other question that comes up. Back in 1947, which was 10 years before Sputnik, we didn't know there were planets around other stars. And we really didn't know what the surfaces of our planets were like in our solar system even. So we hadn't really explored our solar system well. So we didn't know a lot of things. Now in that intervening time, we've explored our solar system with robotic probes. We've detected planets around other stars. And then now so two of these things that have to change your worldview have been bridged. I think of them as bridges. So what else can you bridge? What's the probability that somebody might undertake interstellar travel? We often think that's not possible because we don't do it. Why? Because it's super expensive and we'd rather spend money fighting each other. That's basically what happens. And so it's hard for us to imagine somebody else is going to be different, which is a little sad because I'm hoping that somebody else will be different. And then the last one is you can't traverse these interstellar distances. And that's one of the reasons, the second reason why I undertook that project to model galactic colonization was to show it is possible. So once you can show that these the hang-ups that people have in changing their worldview, once you can help bridge those, then it's easier for them to accept this new view. Nobody's just going to change their beliefs dramatically. You have to kind of lead them along and help them do it. And I think that's what we need to do here.
I think we got time for one more we can squeeze in here. And this one comes back to the question about witness testimony. When it comes to witness testimony, is it not true that a lot of physicists kind of look down on the more anecdotal data of field biology and ecology, medicine, anthropology, etc.? Has astrophysics created a barrier, and I think it continues on the other side, to UAP research by their reliance on signals equipment?
It is true that physicists look down on anecdotal data used in other fields. Physicists are some of the most egotistical people I know, seriously, and I know a lot of them, so I think that I'm qualified to say that. And yes, they look down on the other fields. They look down on other subfields in physics. I mean, depending on what field you work in physics, there's some kind of hierarchy, and it's different depending on who you talk to, of course. So has astrophysics basically caused problems by relying on signals? I wouldn't say that because that's all astrophysicists can do. They basically, what can you measure if you're studying something, from another star system? You can measure light, and you can measure a different color of light, and maybe another color of light, and so on, and now gravitational waves. And in some cases, by looking at the light, you can infer what the magnetic field is like. So, and maybe the electric field. So there's not much to look at except these signals. And so I don't think that's unreasonable. I wouldn't put that on astrophysics at all. But I think that, the fact is that when it comes to UAP studies, we have a whole lot more than just anecdotal data. We usually have anecdotal data with hard data, some kind of hard data. So it isn't that, when we had the Nimitz encounter And, we have, the video of this tic-tac-shaped object, and then we have the testimony from David Fravor. It isn't that, like we heard some popular science proponents say, oh, that could be anything. No, it couldn't be anything, because David Fravor, you see what it's shaped like in the video. It's shaped like a tic-tac. And David Fravor also witnessed this and said it was tic-tac shaped. He described it quite well, actually. And so it can't be anything. You've got the anecdotal data with other data. And especially if they are commensurate, then you can treat that anecdotal data as being more relevant. I don't see any problem with that.
I think you've been addressing not only some of the most pressing issues regarding UAP research, but really in modern science. So I commend you, and I want you all to please join me in thanking Professor Kevin Knuth for an excellent, excellent talk.
Thank you again, Kevin.
Thank you so much.